In this video, we're going to examine the assumptions of the classical regression model in the case of a bivariate regression relationship.
What we're going to talk about now are the ideal conditions that guarantee that the estimated parameters are unbiased, consistent, and attain the lowest variance among linear unbiased estimators. That's also known as the property called BLUE, which is best linear unbiased estimator. The theorem here is the Gauss-Markov theorem because it's based on work by both Gauss and Markov. We're going to start by assuming that there is in fact a linear relationship between our dependent variable and the independent variable in the population. The second assumption we're going to make in this model is that the expected value of the population error term is 0. When we try to get an estimate of the parameters, we're going to be doing that based on the assumption that on average the error terms are 0, that the observed terms are just as likely to be above the regression line as below. If the expected value of the error term is not 0, let's say if it's equal to 5, we'll have errors that on average are greater than what we expected, and think about what will occur. What should happen in that case is that the intercept of the regression equation should just be shifted up or down by whatever the actual value of the error term is. So if the error terms on average are 5, the fitted line will all go through the points where the average error term is 5 instead of 0, which will essentially overestimate the intercept of that regression relationship. Most of the time, it's probably reasonable to assume that the error terms are 0, but there are some special cases, some of which you saw in your introductory micro or macro class, where we might expect non-zero average error terms. For example, suppose you're estimating the parameters of a cost function or production possibilities frontier. In terms of costs, the cost function represents the lowest possible cost that you can have for any given level of output. In real-world markets, firms may be producing above that. In that case, the expected value of the error terms will all be positive. Firms are not generally all going to be at the most efficient level of cost. Similarly, in terms of a production possibilities curve, that represents the maximum output you could produce if you use all your resources efficiently. In any real-world economy, the actual values of the error terms in that case will all be negative because you always tend to be below that. We're not going to be dealing, though, with cost functions or with production possibility curves right now. So let's start with the assumption that on average, the error terms are 0. The next assumption we make is that the error terms have a constant variance of sigma squared. So what that means is no matter what the level of x is, the variance of the error terms around that regression line is going to be the same. So what that means in particular is we're assuming that the error terms are what we call homoscedastic. That means that the distribution of the error terms around the regression line is the same at all levels of x. If we have a heteroscedastic error process, the variance of the error terms might get larger or smaller, or it might vary where it gets larger and then smaller in some sort of pattern. So if there's a heteroscedastic error process, the variance of the error terms is going to vary with the level of x. With a homoscedastic error process, which is what we're assuming initially, the variance of the error terms is always the same. Now, just to see why that might be important, if we have a homoscedastic error process, each of the data points contains the same information a priori about where the line is. But consider the diagram on the right. If the variance is very low at low levels of x and very high at high levels of x, what happens is the data points where the variance of the error terms are smaller tell you more precise information about where the regression line is. So in that case, we should probably put more weight on those points because it gives you a more precise estimator that way. So what happens when there's heteroscedasticity is the basic regression model that we're going to develop initially doesn't work as well. We have a whole later chapter, though, where we talk about how we can test for heteroscedasticity, what the implications are if we ignore it, and what we can do to use it to get more appropriate estimators of the regression line. We can get a gain in efficiency if we take the heteroscedasticity into account. and we'll come back to that later. For now, we're going to assume homoscedastic error processes. The next assumption we're going to make is that not only is the variance of the error term constant for all observations, but the error terms are independent across observations. That the error term, let's say if we're dealing with time series, in 1992 is independent of what it was in 1991. And similarly, the error term in 2020 is independent of what the error term was in 2019. So we're assuming that knowing the error term in one period contains no information about what the error terms will be in other periods. Here are two cases where that's violated. The first case is what we call positive first-order autocorrelation. And when that occurs, positive error terms tend to be associated with other error terms right before or right after that are also positive. Similarly, if you have a negative error term, then the next error term in the series is more likely than not to be negative. In other words, when there's positive first-order autocorrelation, the expected value of the error term in time t is correlated positively with the error term in t-1. So if you know what the error term in 1 year is, you can predict what the average value is likely to be in the next period. And that's similar in some ways to heteroscedasticity, in that when there is a sort of pattern, ignoring the pattern will not allow you to get the most efficient estimates. And we'll again spend a whole chapter where we go over what happens when we have a case like this. Positive first-order autocorrelation, where clusters of positive error terms and clusters of negative error terms tend to occur together, not quite in the sine wave pattern that's illustrated here, but we tend to see bunches together on either side of the regression line. That's really common in a lot of macroeconomic time series. And one of the reasons is, if we're dealing, say, with annual data, if we deal with something that makes people really optimistic at the end of 1 year, then at the beginning of the next year, that optimism is likely to continue. And if we're dealing with, for example, consumption, if people are spending more than they typically do 1 year, that optimism that caused that is likely to continue into the following year. Similarly, if people tend to be pessimistic in 1 year, that tends to lead to somewhat more pessimistic spending patterns in the following year. And that would be what we'd see when we have positive first-order autocorrelation. And there's a lot of evidence of positive first-order autocorrelation in many economic time series. Negative first-order autocorrelation is one where the correlation between, or the covariance between, the current error term and the previous error term is negative, which means they tend to alternate in sign. So positive error terms are most likely followed by negative ones. Negative error terms are most likely followed by positive ones. Again, it's not quite as neat as this diagram might suggest, but there is a persistent pattern where more often than not, they alternate in sign. One case where we might expect to see this is in the case, say, of sales of durable goods. For example, if there's something that made a lot of people buy new cars in 2020, then in 2021, there might not be as many people buying new cars. This has been observed to some extent with iPhone and Pixel sales, particularly in the time period when most phone contracts were 2-year contracts. What we often saw is that if a new model came out and people spent more than usual in that year, the following year there weren't as many people buying new phones. However, 2 years later, we tend to see above average phone sales. So we tend to see negative error terms followed by positive ones and vice versa. The next assumption we're going to make is that the x's are non-stochastic, that they're not random. There's two common violations that we have to be concerned with. The first is measurement error, and if we measure the variables themselves with error, that introduces an error term into them themselves and makes them a random variable. The other case is if we have a right-hand side endogenous variable. If the variable on the right-hand side is not only an independent variable that causes the dependent variable, but it is itself a dependent variable in part of the same model, then we end up with an error term from the other equation. In other words, suppose y is a function of x and x is a function of y. If y is a function of x and there's that error term there, and x is a function of y, there's another error term there, which means that the value of x in the first equation will contain some error because of the error in the other relationship. For now, we're going to assume that there is no measurement error and we're not dealing with endogenous variables. Both of these conditions are going to be relaxed later, and we have a whole chapter devoted to that, just as we do with heteroscedasticity and with autocorrelation. So one implication of this is that we're guaranteeing that the covariance between the independent variable and the error term will be 0. Because if the x's are constant, there is no covariance between the error term and the independent variable. If there's a violation of this assumption, for example, if there's a positive correlation between the level of x and the level of the error term, if the true relationship is given by the line, which is labeled true relationship, what happens is that at low levels of x, the error term would tend to be negative. At high levels of x, it tends to be positive. So what will occur then is that the estimated relationship will tend to have negative errors at low values of x, positive error terms at high values of x, and if we fit a regression line through it, we're going to be overestimating the actual slope. For now, we're going to assume that that condition holds and that the independent variables are truly independent variables and they're not random. The last assumption we're going to make is that there is some variation in the independent variable. And the basic reason for that is, suppose you try to fit a regression relationship and the value of the independent variable is always equal to x0. As long as you take a point that goes through the mean value of y, all those equations, all those lines there, and an infinite number of other ones would give you exactly the same fit, because all that matters is that you are going through the average value of y. You can't do any better than that, and all those equations would fit perfectly well. Intuitively, the issue is, if you want to observe how y changes when x changes, you have to observe some change in y when x changes. And to do that, x needs to change. So in general, you can only observe how y changes with x if x changes in some way.